So we can say U is and P is okay. So this E cross H we call as the Poynting vector. Named after the scientist Poynting, who discovered this. And P is the rate at which energy, so let's be specific, the field energy moves around in space, right? So if I would like to know what is the power flow through unit area dA, so the dA vector is normal to this surface of area dA, and say I have my Poynting vector, which is essentially the cross product of E and H. So the power flow is P dot dA. Okay, and remember, since E and H are time varying quantities, this Poynting vector is also an instantaneous quantity, right? So it is telling you what is the rate at which there is power flow in a locality at every instant of time, right? So P is essentially a time dependent quantity as well. So let's state the Poynting theorem, right, to which he is credited for. This is the specific statement that Poynting made. The surface integral of E cross H over a closed surface is equal to total power leaving right. So there are some nuances that physicists try to cover, right, by making this statement explicit to surface integrals, right. So this is to just emphasize that this E cross H is not quite a point form for power, right. So in all situations, including electrostatics and electrodynamics, if I were to use E cross H as a universal expression for power flow, I may get some absurd situations, right? Some of which is discussed both in the Feynman lectures on physics as well as in our reference textbook for this course, right? So it is important to understand that this Poynting vector, even though we have a point form for the Poynting vector saying E cross H, which I can certainly define at every point and at every time instant, is not quite truly a point relation, right? It has to be always in connotation to some kind of a surface, right? And that we are looking at plane waves, and we can ask questions as to how much power is flowing through a certain surface, right? All right. So we now have this relation E cross H for the power flow, and like I mentioned earlier, it's the instantaneous quantity. So if I were to, just like in the case of transmission lines, ask the question, what is the average power flow, right, integrated over a single cycle, what does the relationship look like, right? So without going too much into the derivation here, I'll just state that from the exercise that we did with transmission lines and how you saw that there was a convenient mathematical expression, right, when dealing with phasors, instead of having to do this integral over the entire time period each time, we have a convenient expression which goes like, right, the complex conjugate essentially helps us get rid of the e to the j omega t and the e to the j kzz terms, right, and what we are left with is just the average over a single cycle, right. So I want you to compare this to the average power, which we said was half real of b I star, right. So since there v and I were simply complex numbers, right, phasors, here we have electric field vectors, right, E and H, whose components can be complex, right. So the cross product of E cross H star continues to be a vector field, right. So P average here is the average Poynting vector over one cycle. Right. So this is the average power over one cycle of the EM wave, remember, per unit area, right. So I am able to talk of a power, right, per unit area, because if I were to truly look at the power in a plane wave, because it extends to infinite, right, in the directions perpendicular to the direction of propagation, the net power carried by a plane wave is infinite, right. This is another reason to say that plane waves are not quite realizable in reality, but nevertheless they are a very, very handy tool in order to construct other field profiles, right. I can make use of plane waves to construct other field profiles by linearly combining various plane waves, right. So for the case of the plane wave solution that we are aware of, let us try to implement this and see what result we get for the average power over one cycle. So let's redo the exercise. So we have E naught, this is the magnitude, we have the direction Ex cap, e to the minus j k z z for the spatial dependence and the time dependence. Okay, don't forget the 4 components. Similarly, we have h was e naught over eta e y cap e to the minus j k z z e to the j omega t. Okay, so if I were to perform the E cross H star for the example of a simple plane wave solution, right, we get P average is, so Ex cross Ey is Ez, right. So it's in the direction of the k vector, right. So the magnitudes multiply. I have E naught squared by eta Ez cap, and these two, of course, the exponentials cancel each other out, right. So exponential minus kzz multiplied with its conjugate becomes 1. So this is a real quantity, so I don't quite have to take the real part of this. I just have to add a factor of half in front in order to get the average. Okay, so we notice that the average power carried by a simple plane wave is E naught squared by 2 eta, where eta is the characteristic impedance of the medium, and this P average is in the direction of the propagation vector, right, kz.